Okay, so good morning and good evening. I hope you can all hear me and see my iPad screen. And I hope this technology is going to work as it has mostly so far in this course. Um, okay, so as you can see, I'm going to use my iPad today, but we'll be back to the usual format in Bloomberg Hall on Wednesday. So last time I gave an overview of the various anion phases that we're going to talk about. We talked about the simplest phase, which is the Z2 spin liquid. But to discuss more complicated ones, there's an interesting interplay between the existence of anions, which is naturally brought about by using partons, and what I generally call band topology. That is, even free fermions generally can have interesting topological aspects to their band structure. And then when you put that together with fractionalization and the parton approach, you can pretty much build up the entire library of interesting anionic phases of matter that people have studied over the last 2 or 3 decades. So the first one we're going to talk about is the chiral spin liquid. And then, as I promised in my email yesterday, I would go on to the fractional quantum Hall effect. As I was thinking through, what I need to cover to give a reasonable discussion of these topics, I decided I should also talk about the integer quantum Hall effect, which will actually be closely related to things we'll talk about today. So I'll probably get to the integer today and maybe fractional next time. So it'll be a bit longer before we go on to metallic phases, which is the next and major topic of the course. All right, so to begin with, we are talking about some antiferromagnets, spin a half on, let's say, the square lattice with some couplings Jij, which we leave unspecified. And we are going to use here the fermionic parton approach, where we're going to decompose the spin into a fermionic parton. So there's exactly one fermion on each side, and alpha extends over spin up and spin down. So there's two flavors of partons, fermions, but only one of them can occupy any given site. And just in the case of the Z2 spin liquid, we postulate some, in this case, free fermion Hamiltonian. And we are just going to take the very simplest free fermion Hamiltonian, fermions hopping on a lattice, the square lattice in this case, with some matrix elements, hopping matrix elements Dij. You can add more complicated terms, but this turns out to be sufficient. Okay, and so of course, we don't know that this is a Gauss ansatz for the mean field theory, so that you have to do some detailed calculations. But we don't know, but with the benefit of hindsight and a lot of numerical studies, there are certain Jij for which this is a good starting point. We're also going to make the Tij complex numbers, and this will have at their mean field level, and this will have the consequence of breaking time reversal symmetry. And that turns out to be actually quite important for the structure of the chiral spin liquid. So the system spontaneously break time reversal symmetry and also some kinds of inversion symmetry, hence the word chiral. So it's as if there are spin currents flowing around, circulating in this spin liquid state, and those spin currents have an interesting consequence. So all right. And this is, kind of similar to the fractional quantum Hall effect, where there are charge currents, but here it's just the spin because these fermions only carry spin. Okay, so of course, once you make this ansatz, then there's a emergent U1 gauge invariance linked to the presence of this constraint, which is that I can rotate the phases of F by some arbitrary time and space-dependent phase factor, provided I compensate with the corresponding rotation of the Tij. And this will play an important role later in this lecture. But for now, let's not, we'll just study properties of this. There's already a lot of richness in the set of Tij that we're going to study. Okay, so here's a picture of, let's see if I can make this smaller. Yeah, there we go. Here's a picture of the Tij I want to take.
What is real and what is imaginary?
So T1 and T2
before,
are all.
Jij is real?
Absolutely, Jij is real.
And
so
Tij?
the Tij are shown in this picture. And T1 and T2 are real, but for example, this hopping matrix element has an I in front, and so it's imaginary. So the diagonal bonds are imaginary, and the horizontal and vertical bonds are real. And by making this ansatz, we have broken time reversal symmetry, as you see.
But then I can ask my question: How is this preserved by the gauge transformation? Because the gauge transformation multiplies Tij by a phase.
Right. So right now we're taking a mean field theory with some factors of Tij, and we're going to look at gauge fluctuations about this mean field saddle point. And so there will be a gauge field, which will be. So eventually, what we're going to do is we're going to take the actual Tij. Tij will be the Tij is shown in the picture. Let me call the Tij bar times e to the I Aij. And this Aij will become our gauge field. This will be our gauge field, and its action will have terms that break time reversal. Okay, but for now,
so before you go to mean field, Tij are arbitrary complex numbers.
In mean field theory, yeah.
And only in mean field theory, they take the values in the figure in the next slide. Okay, thank you.
Correct. Right now we talk about mean field, and then when we include these fluctuations, then the action for Aij will have terms that break time reversal symmetry.
Okay, thank you.
So this seems like a rather dangerous thing to do, but we studied this in the case of the Schwinger boson approach for the Z2 spin liquid. There we found eventually there was a Higgs mechanism that broke U1 down to Z2, and that protected the gauge fluctuations. You're right, in this kind of theory, if there's an unbroken U1 gauge symmetry, in most cases, in fact, you can't ignore the fluctuations. These fluctuations are extremely strong and actually change the picture a lot. But as we'll see today, well, at least I'll appeal to results in the literature mostly. If you make the Tij complex, then the Chen-Simons term can help prevent strong fluctuations of the Aij. It preserves the mean field saddle point in a reasonable way. Okay, so anyway, right now we're not worrying about gauge fluctuation. We're just talking about the mean field theory, and that already has some highly non-trivial structure that I want to discuss, which was, I guess, in a different context of the integer quantum Hall effect, first discovered by Thouless et al., for which was cited in Thouless's Nobel Prize. So that's what I'll just talk about now. So here's a mean field Hamiltonian with these hopping matrix elements. Some of them are real. I mean, the horizontal and vertical bonds are real, and the diagonal bonds are complex, imaginary. And these are all chosen so that if I go anti-clockwise around any triangle, I always pick up the net factor is minus I. So if I go around this way, this is +1, I, and I'm going the wrong way, so that's minus I. If I go here, you will see it's I +1, -1, so that's minus I, and so on. You can pick any triangle you want, and unless I made a mistake, you get a minus I around every triangle. Okay, that's minus I, and so on. So this is sort of like a particle moving in a magnetic field. It's a uniform magnetic field, so that the flux through any triangle is exactly pi/2. Now, similar phenomena also appear in cases where the T is complex, but there is no uniform magnetic field. For example, you could have chosen a different ansatz where some of the fluxes are +I and the other fluxes are -I. And that is what Haldane pointed out later. So that's like a problem in a zero magnetic field. And in that case, also, you will get the phenomena I'm going to discuss. And that was also mentioned in Haldane's citation. All right, so you go ahead and you have a Hamiltonian here of these hopping matrix elements. You can diagonalize it. So let me at least write down the Hamiltonian that you need to diagonalize. So the Hamiltonian, you can write in this way. Let's see. So the Hamiltonian for the fermions has a sublattice index, F dagger A alpha MAB of K and FB alpha of K. So the spin index is not going to play any role here. It's just going to go along for the ride. But there's a sublattice index. A equals A and B are equal to A and B. And I've chosen this ansatz here so that everything has a periodicity of translations along the diagonal. So if this is my A sublattice, then that's a B sublattice. And you can just notice that the environment around this A is the same as the environment around that A. They're exactly the same. So it has a double unit cell, and there's two sites per unit cell. And that's also going to be important for what I want to talk about. So this MAB, you can write, let me just write it down for you. It's good to have it written up. So it's minus 2T2 sine kx plus ky minus 2T2 sine kx minus ky and here it's, well, sorry, and this is minus 2T1 cosine kx plus 2I T1 sine ky. And then you'll get, that's one column of the matrix. It's a 2 by 2 matrix. There's two other matrix elements here. This is, of course, the complex conjugate of the other one. And this is the negative of the other one. Okay, so there's a matrix that you have to diagonalize. And when you diagonalize it, you get two bands because there's, and here's the band structure. Here's the upper band. Let's see, hopefully you're seeing what I'm seeing. Yeah, so here's the upper band. And then there's a lower band, which is just the mirror image of it. And the chemical potential is in between. So there's a gap at zero energy, and the chemical potential exactly at zero. So, all right. So you notice some interesting things. There's a deep minimum here. And if you look at the dispersion spectrum near the minima, you'll find it has a structure of a massive Dirac fermion. But I'm not going to use very much about that right now. All right, so this matrix MAB has certain important properties. And what TKNN pointed out, that any such Hamiltonian, in this case it's a 2 by 2 matrix, but you could take 3 by 3 or even an infinity by infinity matrix, has certain features. And in fact are characterized by a topological invariant. Now, in most cases, that invariant is just zero, which is why it wasn't noticed till 1980. But in some cases, that invariant is an integer, which is non-zero, and then you have the interesting properties that we are going to discuss. So, what are the important properties of MAB? So first of all, one of them, is that it's periodic function of K. So there's a reciprocal lattice, and MAB of K plus G is MAB of K. So this tells us that K and MAB of K lie on a torus. So I'm going to restrict myself to 2 dimensions here. So there's some, well, in this case, there's some unit cell that could have strange shapes in different lattices. So this is K here, then this line is K plus G. And similarly, this is KP here, This is some P plus G prime, where G and G prime are reciprocal lattice vectors. And this region here, which is the fundamental domain of the torus, is what we call the first Brillouin zone. All right. So MAB is a function on this Brillouin zone. It's a function on a torus, and it's a completely periodic functions on a torus. The other important point is that if you look at the eigenstates, so MAB will have some eigenstates for each k. So there'll be some eigenstates, which are, of course, the block functions. They'll be labeled by some integer k, n, and the wave vector k. So n is, 1, 2 in our case, but in principle, it can be any set of integers. And these eigenstates are only determined modulo a phase factor. You can multiply them an overall phase factor as you wish. And now it turns out that there's some uncertainty in that phase factor, and there's some interesting structure associated with that. In particular, if you determine this set of eigenstates n of k, then n of k plus g well, the Hamiltonian itself comes back to itself. The matrix MAB comes back to itself, but there's no reason for this to come back to itself. So it should be, I'm assuming here the eigenstates are non-degenerate. It should be equal to n of k up to a phase factor. Okay, and of course the interesting topology arises from the fact that in some cases it's not possible to make this phase factor trivial. There's always some winding in these states as you go around the torus. Okay, so and that's the topology that we're interested in. It's characterized by the Chern number. Okay, what was I going to say? Right, I forgot. Okay, so these are the important facts, and what TKNN showed that any such band structure. Oh yeah, I was going to draw a picture. So one important assumption here is that there's some eigenenergies En of k as a function of k. Let's start from 0, and let's say this is G. I'm just drawing a one-dimensional section. And you have some band structure. You can have any shape it wants. Comes back to the same point, and here's another band. Come back to the same point, and so on. And the important point is that the bands don't close. So there's a whole bunch of bands, and there's always a gap between them. And they come back to themselves. The eigenvalues come back to themselves, but the eigenstates come back to themselves up to an overall phase factor. Okay, so under these conditions, we have a topological invariant. Okay, what did I do? Okay, so I'm just going to write down the topological invariant as a kind of and I'll refer you to the notes for a proof. It's not that difficult, but the notes are on the website for a proof that, in fact, this is a topological invariant. So let me make sure I get all the factors right. I have to look up. Yeah, so here's the topological invariant. So there's one invariant associated with every band, which is called the Chern number of the band. So you make the band n is characterized by Cn, which is equal to I over 2 pi. You integrate over the first Brillouin zone. And then you into dkx, dky. And then you sum over all other bands not equal to n of the following quantity. So it's a bit of a long expression. The denominator is the difference in the energies. squared. And the numerator is the following object. And okay, more comfortable here. dm by dkx n prime and n prime dm by dky n, and the numerator has another term, which is you interchange x and y. Okay, so that's the famous Chern invariant, first written down in this context by Taulas et al. They didn't call it the Chern invariant because they were unaware that it had been discussed earlier in the math literature, where it's called a Chern number. But anyway, that's where almost all physicists first learned about this. So, so there's a proof. It's not that complicated, relatively elementary as far as these things go, which is in the notes. But let's just notice a few things that at least raise the possibility that this is an invariant. First of all, let me clarify what I mean by an invariant. So I have some matrix M of k, and M of k has some band structure. So now what I say is I'm allowed to keep changing M of k as I want. I keep changing MIK smoothly. I change all kinds of parameters. These bands will move around, but as long as the band gap doesn't close, as long as the bands stay separate, then this integral will not change its value. So that's why you call it an invariant. It doesn't depend upon the band structure at all, as long as the bands doesn't close. And furthermore, it's always an integer. And the integer property follows from the periodicity of the Hamiltonian in the first Brillouin zone and the arbitrariness of the phase by an overall factor. Okay, so first of all, let's make sure that at least it has possibility to be an integer. Just do a dimensional analysis. So the numerator has two factors of m, which is two factors of energy, and the denominator has two factors of n, energy, that's energy squared. It has one derivative of kx and a derivative of ky, and it has integral over kx and integral over ky. So you rescale kx, ky as you want, nothing's going to happen. You rescale energy as you want, nothing's going to happen. But you can even rescale them in a k-dependent way. That's the statement, and nothing will happen. So this value of this quantity is not going to change, provided the denominator stays finite. And that will happen as long as the band gaps remain. Okay, so, and then it's an integer. So that involves a little bit of actual calculation, which is in the notes. So I'll leave it for you to carry out. So it's a fun exercise to actually write a little program for the students. And usually I give this as a homework problem. Evaluate that. Actually, just write a program to write down MAB, which is in the notes, and go ahead and evaluate this integral, and you'll find it's an integer. Oh, another important property of this expression, it's also gauge invariant. In other words, I can change the phase of the ends as I want. You notice that there's an arbitrariness in the phase of the ends here. So I can change the phase of n as I want, but there'll be a compensating factor over here, and therefore that phase will cancel out. So it's explicitly gauge invariant, it's dimensionless, and it's always an integer. Okay. So the existence of this topological invariant has a lot of interesting properties, which we are now going to talk about. All right. But I'll leave the proof in the notes. Okay. So any questions?
I think I heard this sometimes being explained in terms of a Berry phase. What is the connection to that explanation, if there is any?
Oh, yes, absolutely. So the connection is the following. That's in the notes. So you have, here you have a whole set of matrices, MAB, which are a function of K. So think of K as some parameter. So what the Berry phase tells us is how the spectrum of a Hamiltonian and the wave functions change as you change some parameter. So we have a parameter K. Yeah, I may as well write it down. So you have a bunch of state K, N and K, and you can define a Berry connection, so-called Berry connection, which is A N of K, which is the following object. Okay, so you just evaluate how the wave function changes as a function of K. This is called the Berry connection or the Berry phase. It's the Berry connection. The Berry phase is the line integral of the Berry connection. And the Berry curvature, let me call it the B here, B is the curl of A. And the Chern number is the integral of the Berry connection, of the Berry curvature, sorry. So in fact, this is how you prove that this is an invariant. This is, so you compute this is exactly what's in the notes. You compute the Berry connection, compute this line integral is the Berry phase. The Berry curvature is the flux associated with the Berry connection. And the integral of the flux is the Chern number. Yeah, so it's very closely connected.
Subir, how do you interpret the adiabatic theorem in this case? Like, are you moving through K space very slowly?
Yeah, so I think that's a good question. And this is also often very confusing. It also confused me. So the way Berry discovered the Berry phase was thinking about adiabatic processes, which I can mention that in a minute. And he did discover there's a Berry phase in a adiabatic process. But I think a better way to think about the Berry phase, it's just a characterization of the geometry of the wave function. You have some parameter, any parameter. You have some Hamiltonian, which is a function of a parameter. And it has, for every parameter, value of the parameter is it has a spectrum. It is a vector space. I guess I'm not sure. It's sometimes called a section, I believe, because it's arbitrary over a phase. And this space of states has a certain curvature, has some certain geometric properties. And the Berry phase is a characterization of the geometric properties of the space of states. It has nothing intrinsically to do with any adiabatic process. It's just a statement about the space of states of some Hamiltonian. Especially Hamiltonians that lie on toruses or spheres or things like that. Then it's very useful.
Sure. So you don't.
But now you can ask another question. Suppose I vary the parameter as a function of time. So that's the question Berry originally asked, but that's not the question we're asking. And then you compute the change in the wave function as you undergo a loop in parameter space. And when you come back to the same point, you find your wave function as an extra phase factor that you wouldn't have thought just from the e to the minus e to the I energy times time phase factor. And that extra phase factor is precisely this Berry phase. So I mean, I'm not going through that because I don't need to. We don't have any adiabatic process here. I find, when I first learned about it, this confused me no end. But things became clearer when you start thinking about the Berry phase and nothing really to do with the adiabatic process. I mean, it has something to do with it, but it's more fundamentally just a characterization of the geometry of the space of states.
Thank you. That was clear. Thank you. Yeah.
Okay. So here there is a Chern number. So all we need to know that there's a number that characterizes band structure. That's all. Integer. Sorry, there was another question.
Sir, this Chern number that you defined, I assume it's for non-degenerate bands.
Absolutely, yes. I'm assuming that these bands are not touching.
Okay.
Okay, I mean, if they touch, then this expression breaks down. And it's only when they touch that this invariant can change. So now you can ask another question, which we won't ask, but many people have asked this, and there's a lot of theory of it. What happens when the Chern number changes? How can it change? And then there must be a phase transition. In fact, it's a quantum phase transition where the Chern number changes. And the Chern number changes by the bands touching. And when the bands touch, there's a massless Dirac fermion there. So you have to consider theories of massless Dirac fermions to see changes in Chern number. We can talk about that later, but I probably won't. Yeah. But here I'm just interested in the case where the bands don't touch and the Chern number simply cannot change as I vary parameters.
Is it easy to see the equivalence between these two formulas?
Yes, that's in my notes.
Okay, thank you.
Yeah. It's not too bad. It just takes a few lines and there's some simple identities. I wrote this formula because it's explicitly gauge invariant, this formula here. This A obviously is not gauge invariant. And then if you take the curl of B, you get some curl of A, you get some expression for B that's also doesn't look gauge invariant, but of course it has to be. And then you have to manipulate it a little bit using what you have to do is you take the derivative of the eigenvalue equations. You take the derivative of the equation m times n is equal to e times n, and then you can relate derivatives of n. You can relate derivatives of m to relate to derivatives of m, and that's always a great thing to do because then the gauge invariance disappears. Gauge invariance becomes explicit. Okay. Yeah, so I'm sorry, I could spend, yeah, it's in the notes. It's all worked out. Exactly the question that Juan asked. Okay, so now we have this Chern number, which is characterizing the space of states, which is great. And now this has some important physical consequences, of course. That's why we are so interested in it. Where did it go? Oh, put it in the wrong place. Yeah. So one of the most important consequences is the existence of edge states. So now imagine I take a finite part of my sample. So I have my lattice, but I have an edge to the lattice. Okay. So here's, let's call this direction ky. This is y, actually, physical direction y, and this is x. And then I have my lattice. Let me draw it in a different color. So I have some lattice here. Okay, so this is really all I have to do. I have to take the Tij I showed you earlier and just cut them off. There's no more hopping matrix elements here. So here on this bound here, T will be 0. That's the boundary. So it's just a hard cutoff. So I have a finite matrix in the y direction. And I put that on a computer and I can diagonalize it. So before I do any work, let me at least say a few things of what I expect to happen. So first of all, what I noticed in this geometry, it's a strip. That momentum along the x direction is well defined. So kx is a good quantum number. Whereas ky is not a good quantum number because there are boundaries in the y direction. And therefore, yeah, well, let's see. So here, if this distance is, say, L, then my Hamiltonian will be some Hamiltonian in general will be M of kx only, not of ky. And it'll be a 2L by 2L matrix. 2L because already, oh, sorry, actually be L. Excuse me, it won't be 2L. It'll be L by L matrix. Whoops. It'll be an L by L matrix because there's just one state on every site, but there's no translational symmetry along the y direction. But it'll be a function of kx. Okay. So what will the spectrum of kx this thing look like as a function of kx? So it also has to be periodic in kx because I still have the usual translational symmetry in the x direction. So if I plot now my energy eigenvalues, there'll be a whole bunch of them, but they only depend on kx. What will I get? Okay, so, well, let's first imagine that this is L is practically infinite. So I don't really, even Kx and Ky are all well defined. So what will happen? Well, I have this band structure here, which is a function of Kx and Ky right here, but I'm only looking at it as a function of Kx. So if I only look at it as a function of Kx, so if I pick a value of Kx, what I'll see is a whole bunch of eigenvalues as I go along this direction. They'll all be there. But because my Kx direction is finite, there'll be some discrete set of eigenvalues in this direction. Well, actually, is that right? Yeah. So I'll get some discrete set of eigenvalues in this direction, but there'll be all of these eigenvalues. And similarly at every point. So what I'll end up seeing, where's my picture? Yeah, so what I'll end up seeing is a band of states. So I'll get a whole bunch of eigenvalues in some band here. In fact, I have only two bands in this case, and probably it's symmetric, but I won't do a very good job of it. I'll get a whole band of states. This will be all filled in with many, many eigenvalues as a function of Kx, because, and these correspond to different Ky. I mean, Ky is not a good quantum number, but it's almost a quantum number, good quantum number. And so the eigenvalue may shift a little bit, but they'll be very dense as L becomes very large. So this is what I would naively expect. And in fact, this is what you exactly get if I took periodic boundary conditions in the y direction. If I took periodic boundary conditions in the y direction, I would see exactly this. But what happens if I don't take periodic boundary conditions, but I take open boundary conditions? Well, I have actually a Mathematica program here, which diagonalized a related Hamiltonian. This is the Hofstadter Hamiltonian. I'll put this on the website, of course. So I urge you to write your own program. This is a really fun exercise. All I did was I took L equals, I don't know, 20 and diagonalized a 20 by 20 matrix and look at the eigenvalues.
Sorry, is the horizontal axis meant to be Ky or Kx? In your plot, the plot you're showing
Sorry,
now?
thank you. That's supposed to be Kx. Yes, so it's Kx and there's different Ki will project into a whole band. All right, so here's a Mathematica program. This is a slightly different Hamiltonian, but you can take the one I have. And that was on a torus. And you do this calculation. Oops, oh my gosh, it didn't get copied. Oh, I didn't check it. Where's the picture? Oh, well. Well, what can I do? I can try sharing it from, let me see if this works. Okay, technology on the fly here. Here it is. So let's see if I can share this. Share screen, host. Oh God, I have to make myself a host. Okay. Let's see. Excuse me. Let me just, I don't want to spend too much time on it. Let's see. Dario, if you're still there, I need to make the other me a host. Let's see. Okay, I think I just did it. All right, share screen. Yeah, there we go. Share. All right, so I presume you can all see my Mathematica file here. All right, so there's the actual Mathematica file. There it is. Okay, so here's an example of what happens. I can't point to the screen here. Well, maybe you can see my arrow. Yes, you can. So here are the bands. This is kx here. This is energy. This thing had 5 bands, but you can do your own thing. What you see occasionally are, at least just one state coming down as a function of kx, crossing the other, and there's another one crossing it. Okay, so, and these states, in fact, are the edge states. And the other important property is, you can ask, why don't they repel each other? Why do they go right through each other as they seem to be going? Well, if you look at the wave function of these states, which is you can go into Mathematica and look at them, you'll find that one of these states is on the left edge and the other state is on the right edge. So there's a state which has only disperses as a function of kx, one of which is on the right edge and the other is on the left edge. And because they're so far apart, they practically cross. Of course, if there was a finite sample, they wouldn't cross and there'll be a very tiny gap here, which in fact is exponentially small in the size of the system. So these are the famous edge states. So, and so this is a really very instructive calculation to do. And let me now, I have to go back to the other, with the other person, other me. Where's the other me here? Make host. Okay. Okay, that somehow didn't go through. Oh, and I made somebody else a host. Oh, excuse me. Okay, that's disastrous. So Hongchul Choi, I made you a host by mistake. So, are you listening? Oh gosh, no, I can't. Dario, are you online? Oh well, okay. So Dario or somebody else, we may have to start the whole session again because I made the wrong person a host. Oh boy, I knew there'll be some. Okay. Good. Somebody made me a host. Thank you. Now I have to figure out which me it is. Okay, it's the other me. All right. So now I have to find me. Thank you. Anyway, so you can make a general argument there. Okay. I don't know why the video was on. Make host. Okay. Wonderful. Okay, so where were we? Yeah, so here I've told you that then the beautiful thing I showed you, in this case, there'll be exactly one state that comes down here and another state that comes up here. Okay. And what these correspond to are edge states. There's one state going, this way, dispersing this way, and the other state dispersing the other way on the edge of the sample. And the fact that they disperse in opposite ways is really just given by the fact that one is dispersing downwards here and the other is dispersing the other. So one is moving to the right and the other is moving to the left, and they also happen to be on opposite edges of the sample. So why do these states appear? Well, our general argument is the following, and it just follows from the existence of this topological invariant. So I told you that there's an invariant that is defined in any sample, which doesn't change unless the bands close. So this invariant, I can imagine this is a very, very big lattice. And there's some big region here, this invariant is very well defined. And then I can think of the vacuum here as also some insulator, but this is an insulator, it's a trivial insulator where the Chern number is 0 because the energy gaps are, at some very high energy. All the states are just flat bands at some very high energy. So I do have a change in the Chern number in this space here and the space there. So if I imagine that the band structure changes very slowly, adiabatically, so I just go from one region to the other, and the local Chern number, however, has to change at some point. And the point where it changes, the gap has to close. So there have to be zero energy excitations somewhere as I go along from here to there. And that pretty much accounts for the existence of these edge states. So here the chemical potential, is sitting right in the middle at energy zero, so right there. And so these are the zero energy states that account for the fact that the Chern number changes from this region here to the outside of the sample where it's zero. Okay, so that's a very powerful argument that tells you the robustness of these states. They always have to be present. You can put in disorder, in fact, but that's a more general argument that I haven't given you. You can even put in interactions. None of them destroy the existence of these edge states. Okay. Right. Okay, so now once we have these edge states, now this is going to tell us, something highly non-trivial about the original chiral spin liquid that we were talking about. These edge states must somehow be present there, but it's not so quick because we do have to think about the fluctuations of the gauge field. And that's the topic we're going to turn to next, which is what about the gauge field fluctuations? But before I go to that, let me try to now write down some theory for the low energy states, for these states. So we assume all the other fermions are gapped and they're sitting here in these bands. And I'm just going to focus on these states here. And as I've argued, these two states must be at opposite ends of the band. Okay, before there, one more thing I wanted to mention, an interesting, the power of this very beautiful numerical calculation is that this is how Kane and Millay first discovered that there was another invariant, which is now called the Kane-Millay invariant, which is in fact has only two possible values, and that's why it's called the Z2 invariant. It's not an integer like the Chern invariant, and that requires spin-orbit couplings and so on, and also leads to existence of H states, but doesn't require time reversal symmetry breaking. And it was discovered, I believe, by doing this type of calculation numerically and seeing these edge states appear, and then later on finding what was the invariant that protected them. So it's always good to get your hands dirty and do this calculation. All right. So what is the low energy theory of these states? So let me first, they're one-dimensional states. They only disperse in one direction. But let me first recall. So suppose I had an electron gas in one direction, in one dimension. So if I had an electron gas in one dimension, K here, so that'll have some dispersion and some Fermi level. And there'll be a Fermi wave vector here and another Fermi wave vector there. So an ordinary electron gas has two Fermi points, a left moving point and a right moving point. Now this electron or fermion gas also has two Fermi points, one moving left and one moving right, but they're physically separated. So one's on the right edge and the other's on the left edge. And so it makes sense to consider a theory of the right edge alone. So you end up with something that's highly unusual. In fact, that cannot happen in any one-dimensional electron system on its own. It can only happen on a one-dimensional system, which is at the edge of a two-dimensional system, that you only have a right-moving fermion. The left-moving fermion is really infinitely far away, so we can forget about it. So unlike a 1D electron gas, which has two, both left and right-moving fermions, I here, in this case, in the CSL, I'm going to pick right-moving fermion alone, right-moving. Okay, so what is the Lagrangian? Well, it's just a right-moving fermion. You can measure your energies from this point, which we take to have the zero energy. So it'll be these fermions F dagger, alpha, the d by d tau minus I. There'll be some velocity, I Vf d by dx of F alpha. So that's our theory for the right-moving fermion, and it's in 1 + 1 dimension. So this is a chiral fermion because it's only moving to the right, and it can be found at the edge of any Chern insulator. So this system which has a non-zero Chern number and which is an insulator of free fermions, it's called a Chern insulator. All right, but this is not the whole story because that is not the correct description of the edge states of the chiral spin liquid. This is the correct description of the edge states of a Chern insulator, if you happen to find a Chern insulator, which these days people are finding in graphene. But it's not the complete theory of the chiral spin liquid. And the reason, of course, is the gauge field. So now I have to consider the gauge field. So now we're going to get to some more non-trivial. So now we're going to go to the anion part of it. These fermions are partons, they're not electrons. And so now we have to combine the existence of these edge states and the band topology of the partons with the gauge fluctuations. So the gauge fluctuations I recall were Tij goes to Tij e to the I Aij. And in the continuum limit, this gives you a vector field A, which transforms as A minus the gradient of phi, where phi is the naive continuum limit of the gauge transformation here. So unlike the Stringer boson case where we had to worry about very complicated gauge transformation, here life is very simple. I just take this long wavelength limit of phi. And also there is a time component to this, which comes from the Lagrange multiplier that imposes this constraint. And so we won't, we'll just keep, it's exactly the same way and we can figure out all its properties in the usual way. So what do we have to do now? So what we have to do now is get some effective Lagrangian for the gauge fluctuations. Now this will be in 2+1 dimensions. We're in the bulk, we're not worrying about the edge right now, and ask what is the effective Lagrangian for this. All right, so what do I have to do now? I have to, and we're going to just expand this in powers of k. So I have a shift in A here, and a shift in the hopping matrix elements because of Aij, and I'm going to take some long wavelength limit. So in fact, I'm interested in the case where A is very slowly varying in both space and time. Now, what happens now? So what this A, as you can see from this expression, changes the hopping matrix elements. So when I change the hopping matrix elements, I'm going to change also the values of MAB. So let's take A to be essentially spatially uniform for now and slowly varying in time. That turns out to be the most important case. And so in this Hamiltonian, what's going to happen is that MAB is going to change, and it changes in a very interesting way. It changes. So let me see. Yeah, let me erase this because this will come later. So what happens when I make this change is that MAB of K, the matrix MAB of K, goes to MAB of K plus A. It's just a shift in the wave vector because of the way it appears. You can already see it from this structure here. And that's approximately equal to MAB of K plus A dot dm dk. Okay, and various other terms that don't matter. Okay, so now this is very significant, and now you notice something interesting. This shift in A, the shift in the Hamiltonian of the fermions, involves the derivative of m with respect to k. And curiously, and this was the very important observation of TKNN, it's exactly the same thing that appears here in the Chern number. Okay, so now what you have to do is here I've coupled. So there's a fermions in multiplying all of this. Everything in here is being multiplied by f dagger f. Everything here in the Lagrangian has an F dagger here and an F here. So I have a coupling of the fermions to the gauge field. It's F dagger A dot dm dk times F. So if I draw that as a vertex, I have a gauge field. I have the fermions F dagger, and this vertex here is dm dk. Okay, wonderful. So now all I have to do is okay. Where did that go? Oh yeah, all right. All I have to do is compute. I want to now determine the effective Lagrangian for L in 2 plus 1 dimension of it. For A, excuse me. Well, what is that going to equal to? Well, I have an A here. I have a fermion loop. So a fermion loop here, and then I have here a dm dk. Okay, so you evaluate this for the case I'm interested in, and you get a term which will be something like this. It will be I hope I get it right, I over 4 pi, and it'll be ax d by d tau ay minus x goes to y, and I'm not including the contributions coupling to ax and ay. So this is ax comma y, and this is ax comma y. And then you get a coefficient, which I'll call c. So that's a number, it turns out to be a number. And what is that number? Well, very beautifully, this is what Thouless et al. Showed. It's sum over the occupied n of Cn. So that's a really important result that the Chern, so this kind of term is called a Chern-Simons term in the field theory literature. And the coefficient of the Chern-Simons term for the internal gauge field of the chiral spin liquid is just the sum over the Chern numbers of the occupied bands. All right, so this is also, I mean, I think I've outlined all the steps here. It's really not a difficult calculation at this point. And again, it's in the notes. I've shown you how you get factors of dmdk. There's a dmdk here. There's a factor of dmdk over here. And then, you have a state n running through this state and a state n prime running through here. And you just evaluate the one loop diagram, nothing more complicated than that. And then you evaluate it for small frequency, and lo and behold, you get this answer. So where, you can see, you will get exactly from the Kubo formula, exactly this expression for that appeared here in the Chern number. This will just appear exactly from that one loop diagram. Okay. All right. So that's, an amazing connection between very different pieces of physics, all coming together in a really beautiful way, I think. One is the Chern invariant of any band structure. I should say the Chern invariant, is zero often. And if you have time reversal symmetry, it's zero. But if you don't have time reversal symmetry, then it can be non-zero. Later on, as I mentioned already, Kane and Millet discovered a new invariant, which is non-zero even with time reversal symmetry. Okay, but that has had, that is not important for the anionic phase that we'll talk about. All right, so what we have shown here that there's a Chern-Simons term that's present in the bulk theory for the gauge fluctuations of the chiral spin liquid. So in fact, you can also include a tau and by gauge invariance, and this is usually the way you'll see it written out. So L2 plus 1 of A will be I times C over 4 pi times epsilon mu lambda a mu d nu a lambda. Okay, now this term here is the famous Chern-Simons term, and if you can check it, you'll find it is indeed gauge invariant. But interestingly, it's only gauge invariant up to a surface term. And you need, okay, and that lack of gauge invariance up to a surface term is intimately connected to the edge states that we found here. Those are two sides of the same phenomenon. In fact, there's a deep connection between them, which people like Ed Witten and Larry Seiberg have talked a lot about, which is that you can show that the edge states must exist simply by requirements of global gauge invariance. I mean, the original lattice model we're starting with here, is explicitly gauge invariant, but that requires, of course, the edges. I have a Hamiltonian here right down with the edges. It's gauge invariant. I mean, I can just see that. It's totally explicit in the lattice formulation. Adding an edge doesn't break gauge invariance. But when you take the continuum limit and look at the fluctuations, you seem to get an effective theory it's gauge invariant up to a surface term. But we know that the original theory we started with was fully gauge invariant, and therefore there must be something on the surface that makes this thing gauge invariant completely, not just up to a surface term. Okay, so that's another argument for the existence of the edge states. All right, so now, so that's our effective theory. Of course, there'll be other terms that we won't worry about so much because they have higher gradients. As usual, there'll be terms like, del cross A squared, and the electric field squared, which would be dA tau by dx minus dx dAx d tau squared, and so on. But these all have two derivatives, so not as important. Okay, so now continuing our discussion of the bulk, what does this mean? What does this Chern-Simons term imply? So here I am going to punt, so to speak. I'm using an American football term, actually. All right. I don't know what the equivalent term in cricket is. Anyway, I'm not going to go through a discussion of Chern-Simons gauge theories. I think you can find it in many places. And in fact, there are also notes that I have on it. And we're not going to talk about rather different topics in this rest of the course. But let me just make a few remarks on what the consequences of this Chern-Simons term are. Well, it has so consequences in the bulk. I will talk about explicitly.
Can I ask a question about what you said so far?
Yes, please, go ahead.
Is it meaningful to ask whether the particles that participate in the edge states are the fundamental electrons or these quasi-particles of F? Or maybe this is not a meaningful question.
It's a meaningful question. I'm going to come to it. But before I get to that, let me just say what's happening in the bulk. That is the part of theory that I will discuss. Okay. But let me just now forget about the edges, where there's all these subtleties on edge states and gauge invariance. And let me just ask, does this Chern-Simons term for now have any consequences in the bulk? All right. So in fact, it does have very strong consequences. So what are the excitations in the bulk in our mean field theory? So in our mean field theory, we had, okay, forget the edges here. So let's just look at this picture. We don't worry about these states. So in the bulk, there are all these excitations here. There's an excitation above the cap, and these are the spin-ons. So the excitations in the bulk excitations. So there you can create an excitation here if that was unoccupied. So this would be an F alpha, and you call that a bulk spin-on because it's carrying spin a half, and it's a fermion. In the case of the Schwinger boson theory, it was a boson of the Z2 gauge spin liquid, and it was a spin-on, which carries spin a half. So here we found fermionic spin-ons. But now this is not correct. This object here, this gapped excitation you can create in the bulk, is in fact not a fermion. And that's the consequence of the Chern-Simons term. So what happens is that F alpha, the spin-on, F alpha becomes, in this case, what people sometimes call a semion. Okay. So where does that happen? Well, that happens, of course, because of this all-important Chern-Simons term that we have deduced in the bulk. And also in this case, what is the value of C? We have to specify the value of C. C turns out to be 2 for the chiral spin liquid. When we talk about the fractional quantum Hall states, it will have other values, but right now it's 2. And why is it 2? Well, because for the band structure I showed you, this band structure here, so this is the band. This band has, you can compute it, Chern number equals 1. Well, the lower band, this probably has Chern number -1. Well, okay, I'm being sloppy up to a sign. Okay, so it has Chern number 1, this band. And now, so why is the C sub 1, let me call it, the first band has Chern number 1. So why is the total Chern number 2? Well, that's because of the factor of 2 from spin. So I have 2, the F have an index. They have this index alpha here. And I have to sum over them. When I do evaluate this loop here, this fermion loop to get the Chern-Simons term, I have to sum over n. And so C will be 2. And so what happens is that the Chern-Simons term, as the F alpha is moving around, so this is the, so let me at least draw the picture, and I will leave the formal proof for section or for further discussion. Okay. Let me just go to the end of this thing. Yeah. So I have, what I want to do is look at the exchange of 2 F alphas. So I have an F alpha sitting here, and I have an F alpha sitting here. And I'm going to take this F alpha around the other, oops. What happened there? I'm going to take it around to this side. Okay. Now what the Chern-Simons term does is it attaches a flux tube to each particle. So as this particle is moving around the other particle, it's as if the particle also has a flux associated with it. And the flux in this case will be, pi, I believe, if I get it right. Yeah, it'll be the flux pi here, so that when you go halfway around, you pick up a factor of I or minus I. So that, and plus or minus I is of course associated with the lack of time reversal symmetry breaking. Depends which way you go around it. So in fact, these objects, which initially were fermions, when you took one halfway around the other, you get a factor of -1. Now you get a factor of plus or minus I. And that's because the Chern-Simons term has the effect of attaching some flux to each particle. So this, as this particle is moving around, it sees a net gauge flux associated with the other particle. So there's this charge flux composites that you get in Chern-Simons theory. Every time you have a charge, that charge also is carrying a flux. That's kind of what the Chern-Simons term does. Okay, so I don't want to spend more time on that. You know, naturally you could teach a whole course on this and its non-abelian generalizations, but I just want to move on to something actually which is also of equal importance, which is what happens on the edge. So what is the edge theory? And this is related to the question that Nadi just asked. So the edge theory, I told you, already? Well, it's just I have two chiral fermions, F alpha. And I'm going to leave a little space here, d by d tau minus I VF d by dx times F alpha. So that's a free fermions moving on the right edge. I'm just looking at the right edge of the sample. But of course, I have a gauge field here. And as I've said earlier, the gauge field acts on the edge and also on the bulk. It has to act on everything for us to have total gauge invariance. So the gauge field must also couple to these edge states that we found when diagonalizing the band structure of the partons. So how does it couple? Well, it's easy to figure that out. You just by gauge invariance. So it'll be minus I A tau minus I V X minus I AX. The AY won't matter because they're not moving in the Y direction. So this is the theory we have on the edge. The edge theory is two chiral fermions coupled to a U1 gauge field. So this theory is not free at all. It's strongly coupled. I mean, the bulk theory was not free fermions, but apart from that, apart from the change in statistics, it became a theory of free semions almost. But the edge theory now is a highly non-trivial theory. The gauge fluctuations are extremely strong. And in fact, they have a strong effect on the actual structure of the edge excitations. So the edge excitations are not a theory of just two free chiral fermions. Sometimes if you know a little more advanced language, the chiral fermion has central charge. Well, it's half of a central charge C equals 1 theory. So there's two copies of it, but that's not, so that doesn't mean it's half of a central charge 2 theory, as you might, yeah, okay.
Sorry,
and that's because it's
sorry, this little a is the quote-unquote emergent gauge field in the bulk, right?
Yes, it's the same gauge field, but it also couples to the boundary fermion.
Good.
Yes.
So what exactly are its boundary conditions on the edge?
The boundary conditions, well, it's the same as in the bulk. I mean, it's defined modulo 2 pi, but that won't make much of a difference here, as we'll see. Yeah.
I'm sorry, I can't hear this noise outside.
Okay. All right. Maybe it's my headphones. Can you hear me now?
I can hear you now. Yeah.
Yeah. So, well, okay. The boundary conditions define modulo of 2 pi. So I suppose if you put the boundary on a circle, then it's up to
Right, but the boundary is parameterized. So let me see if I understand. The boundary is parameterized by x and tau.
Yes. Yes.
Okay. So are there any boundary conditions on a tau and ax or not?
Well, let's put the boundary theory on a circle, and then everything is periodic modulo 2 pi for the gauge field.
No, I meant boundary. I meant boundary in the sense of the boundary of the bulk. So there's a bulk, and the boundary is parameterized by x and tau, and we can let x be a circle. So I'm asking, what are the boundary conditions on the gauge field? So F is a field that appears on the boundary.
Yeah, and A is the boundary of the bulk gauge field.
Okay.
Okay. It's just whatever it is on the boundary. And yeah. Okay. All right. So this is again where all right. So this is a strongly coupled theory on the boundary, but it's a theory that's exactly solvable. People have different ways of solving it. And the simplest way that I know of is to use techniques of bosonization and Luttinger liquid theory. So this is a chiral Luttinger liquid, which has been coupled to a U1 gauge field. So I'm just going to use that method, and I'm sorry for the students, I'm just going to apologize. If you don't know Luttinger liquid theory, well, I don't know of any shortcut at this point to fully explain what happens on the boundary. Yes.
Sorry, so we're a little confused about why there are two fermions here. What are the two fermions?
That spin up and down. Yeah, F alpha has, there's two of them because there's a spin index.
And how are they
So
coupled?
they're coupled via the gauge field, that's it. There's no couple. There could be other terms you can add, higher order terms, but none of them would be very important.
But without the gauge
exchange,
fields, they're not coupled without the gauge field.
Without the gauge field, then they were just free fermions, just like a free Fermi gas would spin up and down. Yeah. It's like one, yeah. They're both right moving, though. That's the important thing. In an ordinary electron gas, you'd have a right moving fermion spin up and down, a left moving fermion spin up and down. This is a chiral gas, which has only right moving fermions, both spin up and down.
I see. Thank you.
Okay. And they're coupled to strongly coupled to an emergent gauge field. All right. So
I'm sorry, I'm still puzzled by this. This theory, if I just think of it as a 1 + 1 dimensional field theory, is not consistent. It has an anomaly. If I think of AX and A tau as being dynamical fields.
Yeah.
I can think of it two different ways. One, AX and A tau are classical fields, and then it is not strongly coupled. Or I can think of it as A tau and AX being dynamical fields, and then it is inconsistent, and I need to specify more information. But what I don't see is how you can treat it as a strongly coupled quantum field theory.
Well, okay, let me go to the next step, and maybe you can help me say it better. Okay, let me make one more step, and perhaps that'll I'm sure you're right, and but let me take the next step and express things in terms of bosons, and there is an anomaly. I agree, but okay, all right. Maybe I haven't got everything right. Let me just take one more step, and then you can help me. All right, so let's go back to the original theory, which was just free fermions. So I have to now introduce the techniques of bosonization. So I had a theory which was just free fermions, which is F dagger alpha. So here at least I'm on firm ground. Okay, so this theory is exactly equivalent with free fermions. Now you may know that in 1D, free fermions are the same as free bosons. So this is a theory equivalent to a theory of two free bosons with the following Lagrangian. And let me make sure I get all the signs right and everything. Get my notes up here. Not there. All right, so the boson theory of the edge will be 1/4 pi. There'll be some velocity of dx. I'll use the funny phi here. So, and it has also a spin index plus I dx phi alpha d tau phi alpha. Oops, yeah, okay. So this is the boundary Lagrangian of a chiral boson theory. Right, where you have some scalar field phi, which is defined modulo 2 pi on a circle, and its correlation functions completely reproduce the correlation functions of the free fermion C. So these theories are exactly equivalent. You can compute the partition function and see that they're exactly the same. There's one such example in my book, and I think you have to take anti-periodic boundary conditions of fermions to get periodic boundary conditions on the bosons. All right, so you have one boson for spin up and one boson for spin down. Okay, so these are free chiral boson with some Fermi velocity, which is equivalent to a free fermion. And this can be, shown at the level of the states. The eigenvalue is the same. The spectrum is the same, and so on. So then now we have to put in the gauge field. So what does the gauge field do here? So let me just assert the result, and then I think Nadi can help me clarify what I really should have said. Okay, so the result is that this gauge field couples to the following term: I over 2 pi epsilon mu nu a mu d nu phi alpha. Okay, so the gauge field here is coupling to the fermion current, and the expression for the fermion current in the Bose language is exactly epsilon mu nu d nu phi alpha. All right, and I think you're right. So if I look at this term, it's not gauge invariant up to a boundary term. Again, this is in 1 + 1 dimension, and I think that's what you were referring to, Nadi, but please help me. So this is where I've gotten. What I'm going to do now is I'm just going to claim that the integral over mu tells me that what it's multiplying, it must be 0. And that's really all I'm going to use from the gauge field. It's going to impose a constraint on the boson. That much I think is correct, but I may not have said it correctly. So Nadi, I don't know. Can you restate your objection, and maybe I can try to answer it?
Just an objection. It's not an objection. I just meant that it's not a strongly coupled field theory. The theory on the boundary is free, and as you can see also from what you wrote now,
okay.
The Gaussian field, it's a Gaussian field theory.
It is free. It'll become free in the end in terms of boson, but it's not free in terms of fermions. That was what I was saying. It's going to become free in a minute. But as expressed in terms of fermions, is not free at all. It is not a free fermion theory at the edge. It is a free boson theory on the edge, but it's a novel free boson theory. It has, Kac-Moody level k = 2 rather than k = 1. That's all I meant by saying it was strongly coupled. Okay, so maybe I was, well, anyway, so you can see these are rather subtle things, but I think this type of edge argument does work quite well. So now if I look at this, there's only, the only place mu appears is right here. And so this, when I can do the integral over mu, and so this gives me a constraint. So integral over mu tells me that phi up plus phi down equals constant. So that's the beauty of the boson language. What looks very strongly coupled for fermions is very simple. It just gives me a very simple constraint on the boundary bosons, that phi up plus phi down must be a constant. And it's also very satisfying because the gauge field began its life as a way of imposing a constraint. The constraints that f dagger f = 1. And now in the continuum, it's doing something like that, but it's something we can now deal with exactly. We can just impose a constraint, phi up plus phi down equals constant. So therefore, I can now go back to my Lagrangian, and I can define, of course, phi up. I can drop the index, phi up equals minus phi down equals phi without an index. And my boundary theory now this is the final boundary theory, and it is a free theory, but it's not a free theory of free fermions. Okay, so that's boundary theory is LB. Well, basically you get a factor of 2 everywhere, but you get some Fermi velocity, which is a factor of 2, but in general, it could be something else. So let me call it VF bar, dx phi without an index squared. But now you have a 2 here, because I 2 dx phi d tau phi. Okay, it's still a free theory with Gaussian action, but an extra factor of 2 that's really important. It's a dimensionless factor of 2, and this 2 is closely connected to the 2 in the coefficient of the Chern-Simons term. Okay, so what we have found now is there's a free boson theory with the sector factor of 2, and now you can compute all kinds of correlation functions on the edge. You can look at the spin correlation functions on the edge, and so there's spin currents that are going on the edge now, which you could measure in an experiment in principle. Nobody's ever done that because spin is very hard to measure, unlike charge. So there's spins, currents flowing on the edge, and spin correlations decay with some strange power laws, which are very different from this power laws of a free Fermi gas on the edge. And all of those can be computed exactly from this theory. And some of that's in the notes, but I save you the algebra. But this is all I want to say. I should say that in the field theory literature, this is sometimes called a Kac-Moody theory, U1, Kac-Moody theory at the edge. At level, it has a level, and this level is k equals 2. Okay, and the fact that k equals 2 is the non-trivial part, which is why it's not free fermions at the edge. Okay. There's a way of, which I think is one of the things that I think Ed and Nadi pioneered in the old days. There's a way of going directly from the Chern-Simons gauge theory to this Kac-Moody level k equals 2, but I've taken a more pedestrian approach of just working with the actual matter fields that are present on the boundary and coupling them to the gauge field and demanding global gauge invariance everywhere. Okay, good. So that's really all I want to say about chiral spin liquids. Oh, that's already 10:30. All right, well, okay. So fractional quantum Hall effects are going to have to wait till next time, but I think that will move very rapidly. First, I have to talk about the integer quantum Hall effect. And the integer quantum Hall effect, we can now view as a special case of a Chern insulator where the band is totally flat. And that actually is more complicated in a way because a totally flat band obscures a few things. But it's really the same, it's like a Chern insulator. It's just that Chern insulators were discovered after the integer quantum Hall effect anyway. And then the fractional quantum Hall effect, we'll see, we can work out the theory of even non-trivial states of fractional quantum Hall effects by this part-on approach that we've used for the chiral spin liquid. It will also be very similar. And I'll go through that next time then. And I'll be back in Bloomberg to talk about that. Okay, any questions? All right, well, thank you very much. And I guess one advantage of using my iPad is now I can, I have a record of what I wrote and I can post this on the website. All right. Okay, see you on Wednesday then.
I just want to correct the reference. I don't deserve credit for this.
All right, well, I'll leave that. That's kind of you to say so, but okay. I guess these are things I learned from, I think, one of your articles, Nadi, anyway. Okay, at least the other way of doing it. This way of doing it that I presented, the more pedestrian approach, I don't know. I guess it's implicit in various papers in literature, but just something I find very instructive because I have always dealing with degrees of freedom that I know are there rather than asserting they must be there because of gauge invariance. Anyway, okay. Okay, see you next week.